Hey there, welcome back to another episode of our problem solving mini series for introductory mechanics. Today, we are going to cover the infamous position, velocity, and acceleration versus time graphs. So, let's just take a moment to take a deep breath and not get overwhelmed at the thought of doing these problems. I feel like these graph problems really they cause a lot of problems for students, mostly because you're taking the equations that you learned in class for, these circumstances where objects are moving, and now all of a sudden you're generalizing them and applying them in a graphical way that's not really comfortable for most people. And unfortunately, professors at almost every single level of physics love these problems because of this reason exactly. Because they're able to kind of extract and do fun graphical things, and also in most STEM classes it's kind of required and expected that you're going to get some graphical practice in those classes, and this is an easy way to do that, and it's a nice simple way when you know what you're doing and when you're teaching the class to get those things kind of checked off your box. So let's talk about the two types of problems that you're going to come across when dealing with these velocity, position, and acceleration versus time graphs. Typically, they're going to be broken up into two categories. So you'll have qualitative and quantitative questions. The qualitative are going to be geared more towards the behavior of the graph and describing the graph using regular language, so just like increasing, decreasing, things like that. And then there's going to be quantitative, which are going to be more like what you're used to, in the regard that you're going to be asked for a number at the end, essentially, or even potentially a whole nother graph. So you could be, given one graph and asked to find and draw what the next graph or should be based on that information. We'll get into more examples. I'm going to be doing a full-fledged example if this sounds super abstract. But the main thing is that all of the qualitative questions are going to be based in the quantitative analysis. So even though they seem like they're just descriptions, they're based in math. So when we go through the examples, we'll start with looking at the mathematical relationships between position, velocity, and acceleration versus time. And then from there, we can kind of pull out what the description words are, and how to make those qualitative leaps.
Okay, so here we have a position versus time graph of some object and just whatever their trajectory is over some amount of time. So let's say that I'm going to ask, my question to you is, what is the velocity at, let's see, what time do we want to pick? Let's do t equals 2. We'll pick an easy one. And you might look at this and kind of your first instinct might be just to go to the 2 and read whatever value this is, and that's 0. So that would be incorrect because what you're reading off of this graph directly is going to be whatever the position is. So basically you're going to have some object that was moving in the opposite direction. The 0 is somewhere here, and then they switch and start going in the positive direction. They hang out there for a beat, and then they decide, oh no, I want to go back one more time. And then this is just where that reference line is. So we want to get to the velocity. So if we look at some equations that we have for velocity, we know that velocity is equal to the change in position over the change in time. And if we then look at what's happening in the graph here and kind of try and think about this fraction of change in position over change in time in terms of graphical terms, that would be the same as the rise over run, since our vertical is x and our horizontal is t. In other words, it's the slope. So from this, I'll just write out in simple terms that this means that, if I could write in a way that is legible, velocity is the slope of x versus t. So then once we've identified that, we've identified what equation and what relationship we can use, then we need to think about how exactly this equation is applied. So we can use this for each time interval where the slope is constant. And what I mean by that is that from 0 to 1, there's a constant slope, which means that the v is not changing at any point in that time interval. Same as from 1 to 3, from 3 to 4, and then from 4 to 5. So all of these are the time intervals where we could use this to solve for velocity. So then, since our point of interest lies within the interval from 1 to 3, we can choose any two t points between 1 second and 3 seconds to solve for what the velocity is. So I'm just going to rewrite that v is delta x over delta t. And if we think about this in terms of how you would write slope values, you're just going to pick 2 points, not x1 in the bottom, t1 in the bottom. You're going to pick 2 ordered pairs and then use those to find the slope. So I kind of chose this interval so that way I could just choose the endpoints. So I'm going to go ahead and choose 1 and 3 to be my t1. So this is -1 and 1, and this guy is 1 and 3. Then I can go ahead and plug those in down here. So we'll get 1 minus a -1 over 3 minus 1 equals, so that'll end up being 2 over 2, 1, and then of course the units up top should be meters. I'm usually unfortunately lazy about doing that, but those should be meters, and for time it should be seconds, so our units also check out that our slope is 1 meter per second, and therefore our velocity is 1 meter per second. Now that we've gone over some of the quantitative stuff that you could do with going from position versus t to velocity, let's talk a little bit about the qualitative stuff. So we do have this option of you being asked to solve for the velocity or the slope from the graph at a specific point in time. That would give you a numerical value. However, it's also very common that you could be asked to say, list or pick all the time intervals where the velocity is negative. So in that case, you wouldn't necessarily need to actually calculate anything, but keeping in mind the fact that velocity is still equal to slope, you can look at the slope of the graph and then determine things about the velocity. So we can see, since the line is pointed downward, this is going to be a negative slope or negative v. This interval from 1 to 3 is positive, and that checks with what we found down here in the quantitative problem we did. Here, the slope is actually 0. That's going to be pretty major key. I feel like that's definitely something you want to keep in mind. I feel like that gets asked a lot of where the velocity is 0, which would also correspond to the acceleration being constant, but we'll get to acceleration next. And then from 4 to 5 would also be negative. Another way that they might phrase this is increasing or decreasing. So we've got positive, negative, 0. That could also be increasing, decreasing, or 0. And then instead of just picking out the sections that are quantitative, they might have you match this to an actual velocity versus time graph. So now I'm just going to real quick erase this stuff, and I'm going to draw a v versus t graph, and I'm also going to erase this guy in case I need that space. Okay, so I'll do the v versus t in blue. I don't know what the scale is going to be yet, because I didn't do this ahead of time. But we do know, I'm just going to continue these lines, that these are where our slopes are going to change. So, real quick, if you were to do this by hand, this is how you would do it by hand, but generally you would just be able to match and be able to pick like that it's going to be negative here, then it goes to positive, then it's 0, then it's negative. But if we wanted to go ahead and find the actual values, which I think is a little bit much for an exam, but is perfectly reasonable for a homework question or something of that nature, we want to go ahead and kind of quickly find the slope for each of these. So 0 to 1, we'll have v equals negative 1 minus 2 over 1 minus 0. So that would be negative 3. So we'll call this negative 3 down here. The other one from 1 to 2 we found, or nope, from 1 to 3. 1, we'll just do it. 3 minus 1, that's a plus 1. So that would be here. We know this guy is 0 since it's flat, but if you wanted to be safe and you don't trust me, v is going to be, so that is 1 minus 1 over 4 minus 3, which is 0. So we'll put the 0 line there. And last we'll do v equals negative 1 minus 1 over 5 minus 4. So that's negative 2, and that would go right here. And then just adding back in those values and the fact that this is now velocity, meters per second. Okay, so yeah, so there could be a multiple choice where you're given the position versus time, and then you're asked from a bunch of different graphs that would look something similar like this to try and find the one that does negative, positive, 0, negative. And yeah, so that's kind of the behavioral stuff. Now let's expand a little bit by now focusing on that you're given some velocity versus time graph. So first, let's just talk about what we can say is the same. So the same way that for the position versus time, that we had that v was delta x over delta t. So we also know from our kinematics that acceleration is equal to the change in velocity over the change in time, which on a velocity versus time graph would also be the rise over run or the slope. So now we have velocity is slope of x versus t, acceleration is slope of v versus t. This, if you're making an equation sheet, might be something worth putting down, because typically when on your equation sheet you're only going to have this equation, which you could use in problems, but being able to link these two concepts together, that equation, a consequence of that equation is that we can do this, is going to be super important for solving these problems. So I'm just going to keep that box there. So with that being said, then all the same types of questions that I said that you could ask going from position from velocity, you could do for velocity to acceleration. So I'm going to do that in maroon, super quick. We're just going to go through, I'll kind of do the same thing where we can break up where the constant lines are to give us our time intervals, and then I'm just going to calculate them all super quickly. So from 0 to 1, we have 1 minus 0 over 1 minus 0, so that'll be a plus 1. And again, our units we have meters per second in the top and seconds in the bottom, giving us meters per second squared, as it should. We have 1 to 3, where we can visually see is 0. So I think I proved myself last time that flat equals 0, so I'm just going to write it. For 3 to 4, we have -2 minus 1 over 4 minus 3. So that would be -3. And from 4 to 5, let's go down a little bit. We have -1 minus a -2 over 5 minus 4, which would give us a +1 meters per second squared. And then we can go ahead and throw that on. So let's see. I'm going to draw this with this 0 here. So we've got T, A is meters per second squared. From 0 to 1, we're at, call this +1, I guess. I didn't scale that right, whatever. Okay, that's going to be +1. Then all of a sudden we're going to jump down to, or sorry, I just missed that guy there. And then from 1 to 3, we're at 0. From 3 to 4 is when we jump down to our -3. And then from 4 to 5, we pop back up to +1. Okay. So that's all well and good. I'm going to erase this because now we're going to talk about how we can go from velocity versus time to position versus time. So position versus time will be in black again, and I'll start up here with that same equation that we used to talk about the slope. But so now, since we have a velocity versus time graph, we need to get delta x by itself in order to get an expression for position. So if we multiply up the delta t, then we get that v times delta t is equal to delta x. What this means in terms of the graph is that, and again, this is for time intervals, where we want to think of these as time intervals, we would take the area between our line and the x-axis. So this, if I wanted to know the change in position from 0 to 1, then I would take this area under the graph. It would give me that. If I want to know the total position traveled throughout the entirety of the time interval, then I would just have to add these areas. One thing you want to keep in mind is, and this should come, I don't think that this comes out when you do it, just because when you're calculating the area, you think of them as positive. But anything above the x-axis will be a positive area, and anything below the x-axis is a negative area. So I'll put area above x-axis, or, oh, I probably shouldn't call it the x-axis because it's technically, we're using x for position and it's a time. So let me call this the horizontal instead. Which would also be the t-axis in this case. I don't know. Maybe that is a little bit more confusing, but I don't want you to just like think x and then think position. I want you to know that it's the horizontal axis. Okay, so area above horizontal, now that I went on that tangent, is positive. Area below horizontal is negative. So now that we know that, I kind of want to do the same thing as what we just did for position to velocity and velocity to acceleration, and go from velocity to position, just so that you guys can kind of see that as well. So we know that we have the same time intervals. So we have 0 to 1, and we need to find area. So our area for that is of a triangle, so it's going to be 1/2 base times height. And our base in this case is going to be 1 minus 0, since that's the time interval that we're looking at. And our height that we're looking at is going to be +1 minus 0. And if we do that, that's just equal to 1/2. From 1 to 3, it's a little bit simpler because it's a rectangle. So that's going to be just base times height, or length by width. Our base here is 3 minus 1, and our height here is just +1, since it stays the same. And that'll just be equal to 2. And again, oh, and I guess the other thing, since we're sticking with our units, is that that's in meters per second, and this is in seconds, so this will in fact be meters when it comes out of here. Okay, I think based on my bad drawing, this should be going, this will be scaled better if this is a question that they're asking, but this would be 3 1/3. It's my problem, so just trust me on it. But we kind of have to go from 3 to 3 1/3, and then from 3 1/3 to 4. So it's not quite exactly the same intervals for area. So what you could have also done, you just want to, for the area part, it's easiest to break it up into shapes that are the easiest to, that you know the formulas for. So even like for this part at the very end, when we go from 4 to 5, I'm going to be breaking that up into a triangle and a square, because I don't remember the equation for a trapezoid, and why bother? So we'll do 3 to 3.33. So that'll be 1/2 base times height. So the base is 3 minus 3. Oh my gosh. 3.33. Okay. And our height is just 1. So that'll end up being 1/2 times 1/3 times 1. So that'll be a 1/6. 3.33 to 4. 1/2. Oh, so this will come out negative with this way that I'm doing it. 4 minus 3.33 times -2. So this will end up being 2/3. 2/3 times 1/2 would be 1/3. So this will end up being -2/3 meters. And then lastly, 4 to 5. And like I said, that's going to be 2 different sections. So our first one will be that square, which is 5 minus 4 times -1. That would be -1 meters. And then 1/2 5 minus 4 -2 minus a -1, which will be 1/2. Okay, so now we have this. Sorry, that was kind of a lot. But now once we have these numbers, then we can start to put together what the position versus time graph would look like. Now, I will say for this, this example in particular that I did, you're not really going to be asked to draw something like this. Sorry, just getting myself oriented here because I'm going to draw it for you anyway. I think what's more likely to happen is a matching question, because now since the velocity is changing, our position versus time, you'll see, won't be just straight lines anymore. They're getting that t-squared relationship because of the acceleration that's present. So that quadratic kinematic equation is going to start to rear its ugly head, basically. But I do still want to show you what this is going to look like. So using the numbers here, I will sketch one for you. And then we'll talk a little bit more about qualitative stuff. Okay, so I quickly drew that graph off of camera. I also caught that I missed a negative sign here, which is just my bad. But let's talk about the qualitative stuff. So, qualitative stuff when it comes to area under the curve is going to include things like knowing that above is going to be positive and below is going to be negative. So there could be some conceptual questions talking about that. I think that this is a little bit of a long shot, but it could be possible, is you can kind of, one of the things you can pick up from here too, from the behavior, is that since velocity is the slope of position versus time, and now the velocity itself is changing, from that you should be able to decipher what the sign of the acceleration is. So we know that position is increasing, so velocity is definitely positive here and here, but at this point the slope starts slow and gets steeper. So in this one, I'll just talk about this one kind of explicitly. So we go from flatter to steeper. And positively, this is going to tell us that we have to have a positive acceleration because the only way to get a steeper slope is that your delta V is getting bigger, which happens from an acceleration. And if it's happening in the positive direction, then we have to be adding positive acceleration in there. Ooh, still in the big one. But this one is positive, but it's supposed to be constant. I don't think that I drew that exactly the best, but we know that it's constant because we have a flat constant velocity on the velocity versus time graph. In this section, we're still increasing, but we do come to a zero spot right here, just momentarily. Then we start decreasing and decreasing again. And then kind of just quickly, so here, where we're still positive right before the zero, now we're going from steeper to flatter on the positive side, which means that we would need a negative A. Maybe I will just write these out. Steeper to flatter, positive is going to mean that you need a negative A because that's how you would decrease velocity. At the other side of the zero, we're going from flatter to steeper, but now we have a negative velocity. So flatter to steeper negatively is going to be a negative A. Which is still true because all of this from 3 to 4 I'm probably going to need to cut some of this out. Oh, so I didn't exactly draw this correct because this 0 point should be happening at that 3.3 here. So technically these should all be in the same time interval. So I'm just gonna do the not great thing of not having the right scale. So that's 3 1/3, that's 4, and that's 5. So that way I don't have to erase the whole graph and do it again. Okay, so then that tracks because the velocity goes to 0 in this time interval and the acceleration is negative. So we're coming to 0 where this comes to 0, and then the whole time the A is negative. And then in the very, very last section, we're going from steeper to flatter with a negative slope, which means that our acceleration needs to be positive in order to make the slope less negative. Okay, so like I said, I think that these are kind of a 3-star problem to go ask directly about acceleration from position versus time, but it's still an option. The more likely thing is that you're going to be working with a graph that's set up in the way that the velocity versus time graph is or the acceleration versus time graph is, and be asked to either directly compute a value, so one of our quantitative examples, or describe one of these behaviors that I just talked about, so one of the qualitative examples. In other instances other than an exam setting, then you might be asked to draw one graph from the other, which would just be repeating those quantitative steps multiple times. And then hopefully avoiding my mistakes as far as scaling. But that takes a little bit of practice, and that's definitely something that's more involved. And I guess the very, very last thing that we can kind of say is that, so I talked about going this way is slope, and going from E to A, from V to A is also taking the slope. And then we talked about how going from V to X is going to be area. Well, that also means going from A to V would also be area. But since those areas would all be square and they're flat, they're much, much easier to see. So since these are so much quicker, this is plus 1. V goes from 0 to plus 1 in that first time interval. This is 0. V stays at plus 1, so we're not adding any area. We would add 0. Then we have negative 3 on this. We go from plus 1, subtract 3 to get to minus 2 in this interval, and then we get another plus 1, so we go from negative 2 to minus 1 as we add that area on. But yeah, that's pretty much all that I have on our overview of position versus time graphs. Practice, practice, practice. I would put money, if I were a betting woman, I would put money that you will see this a couple times. They're just very common. They're very popular problems amongst professors, and you're just bound to come across them. So being able to understand them is going to be super important, and there are going to be more concepts that use and do these sorts of graphical problems as you go through. So just something to keep in mind, and something that a lot of people struggle with. So hopefully this video will help. And as usual, we will cut to Howitzer for our outro clip. See you guys in the next problem solving tip video.
Howitzer. Good boy. Say bye to the kiddos.